to reduce it to make it more simple, right? And what does an equivalent system mean? And I just put the abbreviations ES up here. It means that it has the same resultant effect. And remember, if you remember on these problems, here we were looking for what's the equivalent system at point O, and here we were looking at the equivalent system of point O also. And when we're talking about equivalent system, what are we looking at? We're looking at making sure it has the same resultant. It causes the same translational motion, which is the resultant force, and it causes the same rotational motion, which is the resultant moment. Everybody remember that? So we started, number one, had a beam with 3 forces on, and what did we find that it was equivalent to? Let's go around. Tara? What was this problem equivalent to? What was the force and moment at point O that was equivalent to this problem? Were you here on Tuesday?
Yeah.
What do I need to draw here? Let's go, Mark.
We broke up the 100-ton force.
Okay, but just give me the answer, because we don't have to go through the work again.
It was 10 pounds for the force.
Okay, so 10 which way? 10 up, 10 pounds up, and?
The moment was positive 280 inch-pounds.
280 inch-pound. So we were able to reduce this more complicated problem to just a force and a moment at the point in question. How about this one? We took that. Now the problem got a little bit more complicated because what did I introduce? Chris, do you remember what this is called?
That's just a moment, right?
Right.
Yeah. About a point.
Concentrated moment, right?
Concentrated.
Concentrated moment, just like a concentrated force because it's at one point. And what was this system equivalent to? What did I put it? What did we decide to put at point O?
880, I think.
Okay, 880 inch-pound. And anything else?
You know what? I don't think I wrote down the
Hughes?
force.
10 pounds up. And 10 pounds up. So in the end, we took this more complicated problem and we reduced it to one force and one moment at a point. Equivalent system. We're simplifying the problem. Can you think of another thing that I could do to make another system that's equivalent to this? We said that these 3 forces together created one pull of 10 pounds up, and it created a moment of 280 about point O. Can you think of an equivalent system where I only need to put one force in that system to make it equivalent? So we still have the same dimensions, right? And I'm actually going to put 0 here, C is here. How long is this? 10, 18 inches? Here's another equivalent system, but now I don't want to put just a force in a moment. I want to put only a force. In order to have the same net effect on point O, what force would I put in and where would I put that force? Eric? G?
It would be 280 divided by 18, and then you could figure out your force.
Okay, you have the right idea that you're looking at the 280, right? But think of the force first. What force do I need to put on this?
10 pounds.
10 pounds. So I definitely need to put 10 pounds somewhere on here, right? Because we know that this beam is going up 10 pounds. So Eric, let's go back to what you said. Yes, you're right. You need to use the 280, but you don't want to divide it by 18. What do you want to divide it by? 10. Because you want to find the location of where to put this force. We know that using right-hand rule, The moment is equal to the absolute value of the force times the absolute value of the distance, the perpendicular distance. So if I know the force is 10 pounds, and I know the moment is 280 inch-pound, can't I solve for the perpendicular distance? Wouldn't it be the moment divided by the force, which would be 280 minus 10, which is 28 inches. Right? We know that this beam is spinning 28 inches, inch-pound, and we know it's being pulled up 10. So where do I need to put this 10 now? What did I just determine?
28 inches.
I need to put it out 28 inches, so maybe I need to attach something here. So I'm actually coming out 28 inches. And I'm going to put the force now of 10 pounds. And would you say now that this is an equivalent system as well? I have the same beam. The beam is being pulled up 10 pounds. And how much is it spinning at point O? If it's 10 pounds out, 28, what's the spin here? 280. Right. Now, it looks kind of weird because the force is somewhere off this, right? There would have to be some kind of connection or so that it actually does connect to this and cause it to spin. Okay, so my dotted line is some kind of connection. Peter or Santiago had their hands up. Peter, did you have your hand up?
Yeah, I guess I'm wondering how we're getting rotational motion. That would all be translational only on force.
No, because I'm looking at point O, right? So if I have my finger here holding this beam right here, and I'm taking the 10, and I'm applying 10 pounds, wouldn't it cause it to spin around here? So
Yeah.
remember what we did, everybody take your pen, right? Put your pen down, we use popsicle sticks. Put your pen down, and you're pulling it up 10 pounds and at the same time spinning it. You're pulling the whole thing up 10 pounds, pulling the whole thing up 10 pounds, and you're also spinning it at the same time. The whole beam's going up 10 pounds and it's spinning at the same time. So we started out with a complex problem, which really isn't that complex. There are many others and we'll be doing some more. And we reduced this to an equivalent system having a force and moment at point O. Why did I pick point O? Because the question asked me to pick point O. They wanted me to find an equivalent system at point O. So first we found the force and the moment at point O. Would you agree that these forces here and this force in this moment create the same net effect on that beam? Would you agree? They're both pulling the beam up 10, and they're both creating a moment of 280 about 0. Hang on, David. Then we have another equivalent system. Instead of putting a force and moment at that point, pulling it and screwing it, we're actually just going to pull it, but we're going to be at a certain location. So this is an equivalent system force location problem. I'm reducing this problem to the same beam with one force at a certain distance. Okay, David.
Does this only apply if we're dealing with like a massless concept? Because like once you have a longer beam, doesn't that be more weight? See, the force couldn't equal the same amount as like a beam that has less.
Okay, let's see. And we would always have to take into account the weight of something, but in this case, we chose not to deal with the weight. We made believe that the beam was weightless. But if I had, wouldn't we be doing the same problem if I went to the midpoint? This is 18, right? So Notice, what's it stand for? NTS? Not to scale. It looks horrible, doesn't it? Okay, so if I had a weight in here that was half the length over 2, I could still do that. I have a 50, I have a 60 going up, I have a 100 going down, I have a weight going down. I could reduce this system to this, and I'd have to take into account the weight, that what moment it causes, and the weight and the force. Weight is just another force to put in the problem. I just didn't put it on there. I just showed these external forces. Okay, so now, I want you to do the same for this. This is the problem we did on Tuesday. We had a beam, same 3 forces. In addition, we had a concentrated moment. We reduced it to a force moment at point O. Why point O? Is the problem asking to find the equivalent at point O. So now, let's come up with the same kind of thing. We have a beam. So this was problem 1. Here's problem 2. Point 0, point C, 18 inches. And now I want to get an equivalent system that's a force at a location from point O, because point O is the one in question. So in these 2 cases, I showed a force and a moment at point O, and now I'm showing only a force. Wes?
80,
What?
80 inches, 10
Okay,
pound force.
so how'd you figure it out?
Same exact way.
So tell me, perpendicular distance is equal to
The moment over the force.
the moment over the force, and that was 880, right, over 10, and that's 88
Is
inches?
it 880?
Yeah.
It's 880. So then
That's
it'd
why I
be-
had to do the math.
Then it'd be
because I thought you
88
said 80.
inches.
Okay, so it's 88 inches away,
I
88
wrote
inches
8 on
away.
it down.
And what do I have to do with, where do I put the force? 88
Yeah.
inches away, is it going up or down?
Yeah, it's going up.
It's going up.
For me, I have a hard time seeing that that's the opposite of what Peter was saying. Like, I can only see that that's rotational motion. I can't really see how that's making that whole thing go up 10 pounds.
It's,
Because
It
I'm
is-
just thinking about it like that. But
okay, so take your pencil, put a load on it. The only way that this is not going up is if I hold this. So here, I'm gonna hold this, right? It's connected to my hand and connected to my, if I put a load on it, it's only gonna rotate.
It's
But
not
it's
being
not
held.
connected.
it's just floating. And
It's just floating in space, and when I put this on,
there we go.